Okay, guys, 9 a.m. and we can start. So today we're going to talk about capacitors again, right? So in the previous lecture and the recitation class, we discussed what? We discussed, first of all, we introduced the idea of capacitance. So if you have two electrodes, one is positively charged, one is negatively charged, and of course there will be some potential difference between them, delta V. Then by definition, that's how we define this new quantity. Capacitance was introduced as ratio of the charge versus um, potential difference, right? Okay, then you can apply this definition to find capacitance of anything. Okay, so we applied it for a parallel plate capacitor, and we ended up with the formula capacitance equals to epsilon naught times area of the plates divided by d, which is the spacing between the plates. And what's the major feature of this formula? That capacitance depends only on the geometry. If you build a parallel plate capacitor, you can measure area, you can measure distance, you can calculate and label capacitance, right, of that capacitor. Right, so now, basically now we can say we know how we can analyze a single capacitor, one capacitor. Basically, if you know C, Q, delta V, if you know these three parameters about a capacitor, you know everything about that capacitor. So we can say now, yeah, we can analyze a single capacitor. But what about if you have more than one capacitor? What if you have 2, 3, or maybe 100 capacitors? How can we analyze those cases, right? Okay, and today we're going to introduce the method, some of you of course familiar with this, method of an equivalent capacitor, which can be used to analyze a circuit full of capacitors. But there are significant limitations of this method. This method can be applied only when capacitors are connected either in series or in parallel. And of course, there are plenty of
And of course,
situations where, yeah, hello? Okay, so somebody changed her mind, right? Okay, all right. So yeah, limitations. But of course, there are plenty of situations where capacitors are neither connected in series nor in parallel, right? So what can be done in that case, we will talk later. But for now, only to these situations. If capacitors are connected in series and in parallel, this method can be applied. And we will see how that can be done. Okay, but first we need to derive formulas which can be used and some important pieces of physics which we will need to apply this method of an equivalent capacitor. So let's start first with capacitors connected in series. I drew it in advance, right? So this is the situation when and of course I used the simplest possible situation when we have only two capacitors. Of course you can add, you can have 3, 4, or 100 capacitors connected like this, right? And this is the case when they're connected in series. All right. And so what's the idea? The idea is that you want to replace all these capacitors with a single capacitor, which we are going to call an equivalent capacitor. Okay, so I can redraw that this real circuit can be replaced with a simplest possible circuit where we have only one capacitor, which we call C equivalent. All right. And when you replace these guys with single equivalent capacitor, we must add a very important words. The rest of the circuit, in this case, it's just a battery, but of course, in general, it can be complicated circuit over here, right? The rest of the circuit must work in exactly the same way. Again, in the equivalent circuit. So what does it mean? It means that if in this case, battery over here provides delta V, potential difference is delta V, exactly the same delta V must be here. If a certain amount of charge is taken from this battery, let's say Q, exactly the same amount of charge must be taken from the battery in the equivalent circuit. It's a very important statement. So when you replace capacitors with an equivalent capacitor, the rest of the circuit must work in exactly the same way, because you can spend, I don't know, months building the rest of the circuit, and with this replacement you don't want to disturb it, you don't want to ruin all your work. All right, okay, let me write it down. All right, so I can write, so C equivalent, which we wrote, is inserted, is inserted, okay, I abbreviate, is inserted without changing, without changing the operation of the circuit. Okay, without changing keywords. Okay, okay, so now we need to what? We need to derive a formula which can be used to find this C equivalent. And then one additional piece of physics, which is very important and will be very important, right? Okay, again, since the circuit is full of capacitors, whenever you work with capacitors, you have to discuss three parameters all the time. These three parameters: CQ delta V, CQ delta V, every time. You will sick and tired of me reminding you about that, right? Okay, so uh, we will have to find eventually a formula for C. Okay, so let's just leave it behind, because that's what we will get at the end. So as a result, only two parameters left: Q and delta V, which can be used to derive that formula, right? And first I want to ask, so which quantity, Q or delta V, is the same for both of these capacitors? Sometimes students give me the correct answer immediately, although problems with justifications or explanations why. Sometimes, as I said, students tell me, okay, charge will be the same. Great. Why? Let me explain. Look, what if we take this part of the circuit? Let me use green because I've used red already. Let's use this part of the circuit. You see? It goes through this gap, goes through that gap, that part of the circuit. What can you say about this part of the circuit from the point of view of a electron or electrons? From a point of view of an electron, look, this is the gap which electrons cannot get through or penetrate, right? So this is just a gigantic abysmal abyss for an electron, either filled with vacuum or some dielectric material. And of course, electrons cannot jump through or jump over this gap. From this side also, it's just a gap. Electrons cannot get through this gap. So from a point of view of an electron, this part of the circuit is effectively an island in the middle of the ocean. So and that island cannot be reached, and people or electrons cannot escape from that island. So from a point of view of an electron, this is an island. And moreover, what can you tell about the total charge of this island? Basically, it's a piece of metal, right? What can you tell about the total charge? It must be neutral, electrically neutral, right? It must be an electrically neutral, right? Why? Because, look, for example, here you had a switch. And let's say at the initial moment of time, the switch was open. So the whole circuit was electrically neutral. And just a piece of metal, right, without an additional charge. But once you close the switch, right, so of course, current will start go through the circuit, but electrons cannot get in and cannot get out. So this piece of metal, that island, will be still electrically neutral, right? So this is an electrically neutral island. As a result, now let's, okay, we assume that charge Q left the battery. Where does this charge go? Not much places where it can go. Just go up here and will get stuck over there on this electrode without being able to get through, because this is the gap, right? So as a result, all right, so this charge Q will end up here, giving us plus Q, because yeah, this is a positive electrode, that is negative electrode of the battery. So all this positive charge will end up on this electrode of the capacitor. Now, what will happen on the island? Yeah, it's electrically neutral, but it still has tons of electrons, free electrons, because it's a piece of metal. So of course, those electrons seize this positive charge, because we have basically two electrodes next to each other, right? This gap. Of course, electrons will run to this electrode of to this side of an island, and exactly the same amount of charge, but of course opposite in sign. So if we have here plus Q on this electrode, we're going to get minus Q. Basically, it's an induction of a charge on this side of the island. So it will be just attracted by this positive charge. Okay, great. So now we have a negative electrons will get accumulated on this side of the island. But again, it's still the island is electrically neutral. If we have negative charges on this side, what will be on that side of the island? Positive charges. Electrons will run away, leaving positive charges behind. So exactly the same in absolute value, but opposite in the sign will be on that side of the island. Plus Q. Okay, and then what about this electrode? This electrode is physically connected to this negative electrode of the battery. Of course, this electrode will be charged with minus Q naturally, because just electrons will be able to reach it. So as a result, you see, in these capacitors, charge is exactly the same. You see, plus Q, Q, and you can add as many capacitors as you want, and charge will be exactly the same in all these elements connected in series. So basically, that is the test that you have to imagine and run in order to convince yourself that capacitors are connected in series. Charge is the same. So charge is the same. So that's what we can extract. That's piece of information about the charge. So let me write that down. So Q1 equals to Q2, right? And equals to the charge left the battery. Okay, now let's add an additional very important step. So now we established, so Q1 equals to Q2 equals to this charge which left the battery. But again, you remember when we replace this real circuit with an equivalent circuit, the rest of the circuit worked in exactly the same way. It means that Q1 equals Q2 equals this Q, and exactly the same Q over here in the equivalent circuit. And where does this charge Q go? To the equivalent capacitor. So it means that this equivalent capacitor is going to have exactly the same charge Q. Let me call it Q equivalent. You know what? Let me just Q equivalent. Let me remove this. Let me write just Q equivalent over here. Q equivalent. So it means that Q1 equals Q2 equals to this Q equals to that Q and equals to Q equivalent. So I can add important over here part equals to Q equivalent. So this very important piece of physics we are going to use in our analysis. You will see how. So for now, remember that charge in an equivalent capacitor equals to charges in capacitors connected in series. We're going to use this piece of physics, and very often that's where students struggle. They don't remember this important piece of physics. Okay, so that's what we can say about Q. Now, the next, delta V. What can we say about delta V? Delta V usually simple. Right? Everyone usually sees that. The total voltage drop across the whole circuit, delta V. Okay, let me show it here. All right, so this delta V equals to the voltage drop across this capacitor, delta V1, and plus the voltage drop across the second capacitor, delta V2. So we can write that delta V equals delta V1 plus delta V2. Okay, so now I can write this delta V equals delta V1 plus delta V2. Okay, that's piece of information that we can extract about using delta V. And in this case, actually, we are getting the equation, which is very important. So now we can use this equation to derive the formula which we need. We want to get the formula for the equivalent capacitor. So now let's just write it in terms of charge and capacitance, because eventually we will have to get the formula for the capacitance, right? So let's use the formula for C. C equals a Q over delta V, or delta V equals Q divided by C. Okay, so I can write that this is equal, delta V1 equals to what? Q1 divided by C. Q1 divided by C1, right? But Q1 is equal to Q. So let me, as a result, let me remove this subscript 1. It will be just Q divided by C1. And exactly the same I can write about delta V2. It will be Q2 divided by C2. And again, I will remove the subscript Q2 because we just found that charges are the same. Okay, so that's how I can rewrite this side of the equation. What about the total voltage drop? Total voltage drop, I want to write using the equivalent circuit. Because I want to bring C equivalent into this equation so that I can equate capacitances. So let me write delta V using an equivalent circuit. And again, this delta V must be equal to this delta V, right? Because that's how we develop the method. Okay, so now over here I can write that this delta V equals to what? It's just a single capacitor, so again it will be Q equivalent divided by C equivalent. So it will be Q equivalent divided by C equivalent. And that's what I'm going to use over here, right? So as a result, I can write this as Q equivalent, but Q equivalent again equals to Q divided by C equivalent. Okay, so now let me just rewrite this formula and equation to get the formula which we wanted. So it will be Q over C equivalent equals to Q over C1 plus Q over C2. Of course, Q gets cancelled because it's exactly this, they're exactly the same. And as a result, we're getting the formula which we are going to use in analysis. So 1 over C equivalent equals to 1 over C1 plus 1, 1 over C2. Let me frame it. Of course, all of you, most of you are familiar with this formula. So now, what do we have to remember from here? Of course, the formula which must be used to find the value of equivalent capacitor, and this important piece of physics. Again, usually, I know 99% of students have no troubles, of course, applying these formulas. Okay, based on my experience, right? But lots of issues using that. Okay, so, but anyway, we will practice. We will see how it can be used. Now, let's discuss C equivalent in a very similar way. Again, we want to replace real circuit with an equivalent circuit. It means that if you have two capacitors connected like this, and this, in this case, they're connected in parallel, we want to replace these capacitors connected in parallel with an equivalent circuit where you have only one capacitor, which we're going to call C equivalent. And again, the rest of the circuit, in this case, battery, must work in exactly the same way. Of course, I don't want to rewrite this statement. So it means that if potential difference across this battery is delta V, exactly the same delta V must be here, right? If some charge amount of charge Q is taken from the real battery, exactly the same amount of charge must be taken from the equivalent circuit, from the battery in the equivalent circuit, all right? It's very important. The rest of the circuit must not be disturbed. Okay, and so again, exactly the same. We have three parameters, CQ delta V, again, we will have to find the formula similar to this for C. As a result, we need to start with either Q or delta V analyzing this situation. Let's start with delta V. Because you can see immediately, usually everyone sees that voltage drop across the battery equals to the voltage drop across potential differences across each of these capacitors. Justification is very simple, because let's say this is 10-volt battery. Let's say this is +5, this is -5. So this electrode of the battery, then this piece of wire, then this electrode of this capacitor, then this electrode of this capacitor, they all form just gigantic one big piece of metal. And when these capacitors are full, this piece of metal is in the electrostatic equilibrium. And you remember in the electrostatic equilibrium, potential is exactly the same. So if this is at +5 volts, this will be also at +5, and this will be also at +5. And then exactly the same I can say about the left-hand side of this circuit. -5, and again, this is just one gigantic piece of metal. So if this is -5, this will be also -5, this will be also -5. And again, potential difference as a result, 10, 10, and here 10. So about potential difference, we can write this. So delta V. Okay, you know what? Let me step away slightly. I'm just trying to estimate the amount of space I might need. So delta V1 equals to delta V2, and of course equals to the potential difference across the battery. But now we need to add information about the equivalent capacitor. Which way? Delta V1 equals delta V2 equals to this delta V. But since the rest of the circuit must work in exactly the same, so it must be equal to this delta V. And this delta V is applied directly across a single capacitor. So the potential difference across an equivalent capacitor must be equal to the potential differences across capacitors connected in parallel. This is another important piece of physics which we are going to use, delta V equivalent. Let me frame it. Right. Again, this will be very important step in the analysis, which we are going to make, okay, maybe like in 10 minutes. Start making maybe in 10 minutes. So this is, of course, what I wrote over here. It's basically a test that you have to run to convince yourself that your elements, in this case capacitors, are connected in parallel. If potential differences across devices exactly the same, it doesn't matter what you apply over here. It means that your capacitors are connected in parallel. In series, it's a charge. If charges are the same, it doesn't matter how you drive your circuit. Okay, it means that your capacitors are connected in series. So that's basically the major feature. Okay, so now again, it's very important. Yeah, we're going to use, but what about the formula? We need to get the formula for C equivalent, right? And of course, it must be based on the charge, right? Since we used up delta V, so now we just need to use charge. And charge is reasonably simple, right? Look, charge Q left. Where will that charge go? Of course, it will come here, all right? So let's call it Q1. And of course, some of that will come here, and let's call it Q2. And of course, we can use what is called conservation of charge. If 10 electrons left the battery, probably maybe let's say 4 will come here and 6 will be there. Right? So every time if you add Q1 plus Q2, you must end up with total charge Q, which left the battery. Right? So we can write that conservation of charge, that Q equals to Q1 plus Q2. Conservation of charge. Okay, let me write conservation of. You know what? No, I wanted to write underneath, and this will be in my way. Okay, just remember that it's conservation of charge. Because the whiteboard is so little, right? So every time I have to be very careful. Okay, so now again, I want to write in a similar way, but now I want to get rid of these charges, and I want to write it in terms of C and delta V. Okay, so I can easily do it. So this Q1 will be C1 times delta V1. So this will be C1 times delta V1, right? But delta V1 equals to the potential difference across the battery. So let me drop this subscript. Right. Then exactly the same I can write about this. So it will be C2 times delta V2. But delta V2 again equals to the potential difference across the pattern. Let me also drop it. And now let's write the total charge. And like here, the total charge we can get from the equivalent circuit. From the equivalent circuit, right? So, all right, so I can write that Q will be equal, again using formula, so it will be C equivalent times delta V. C equivalent times delta V, and that's what I'm going to write over here, right? So that piece of information will be here, right? Okay, let me frame it with green, right? And use the same color green here. So it will be C equivalent times delta V. Okay, so now let me rewrite it in terms of these replacements. Of course, it will be C equivalent times delta V equals to C1, times delta V plus C2 times delta V. Where you see immediately we use the fact that all the potential differences are the same. So delta V can be canceled, and we're getting the formula, of course, which you are all familiar with, right? So as a result, we will end up with C equivalent equals to C1 plus C2. And of course, if we have more than two capacitors, so of course it will be plus C2 plus C3 plus C4 and so on. So let me frame it. And so now we're almost ready to start analyzing, right? What we need again every time, these formulas and these important pieces of physics, right? So if potential difference across an equivalent capacitor equals to the potential differences across capacitors connected in parallel. So we need to remember, again, students have no troubles using this and that. As I said, like 99% of students ace it. But once they come to the point where they have to apply this, you will see in a few minutes, that's where a lot of troubles. Okay, enough of the, usually I do it in the lecture, but because we had an exam, so I couldn't do it. And so that's why I derived it here. So now let's look at the example. Where is my example? Just a second. There it is. Problem 57. Very similar, of course, will be on your homework. And second midterm exam, something like this, quite possible. Right, 57. And arrange your page like this. I'm going to draw circuits in the middle. Leave some space above, and of course, plenty of space below, right? And let's start with the circuit. Circuit is, again, as I said, I'm going to draw it somewhere in the middle. All right. I think it should be enough. Yeah. So let's say we have a battery and three capacitors connected like this. All right. So first one, then the second one connected like this, then the third one, and they are connected like that. Okay, now let me label them. So this is delta V, potential difference across a battery. Okay, I will write the values in a second, right? Then C1, this, then C2, and C3. Okay, now let me write the values. Delta V 9 volts. Then C1 4 microfarads. Then C2 12. Yeah, 12. C2 12 microfarads. And then C3 2. You remember units of capacitance farads. Okay, so the question is, okay, yeah, the question, let's say, analyze the circuit, or the order, analyze the circuit. So what does it mean analyzing this circuit? Circuit full of capacitors. About battery, we know everything. Potential difference is given. Okay, so we don't need anything else. So what does it mean analyzing? It's like here, I mentioned already several times. You can say that I know or you know everything about the capacitor if you know C, Q, delta V. So basically, we just, if you know CQ delta V of this, CQ delta V of that, CQ delta V of this, okay, you are the God. You know everything about this circuit. And since information about capacitances are given, so what's left? We need to know Q's in each of these capacitors and delta V's across each of these capacitors. So that's what we need to find. All Q's and all delta V's. So let me write that down. So now basically we need to find Q1, 2, 3 and delta V 1, 2, 3. So all Q's and all delta V's. Once you know that, you know everything about your circuit. Okay, so now let's start applying all this. Okay, hope that it will work because again, limitations, right? So this can be used only if capacitors are connected in series or in parallel. So first, we need to replace this real circuit with an equivalent circuit where you have only one capacitor, equivalent capacitor, and one battery. So let's try to simplify that circuit to the simplest possible. Right. So first, which capacitors are connected either in series or in parallel? I think it's obvious, right? So these two guys are connected in parallel. So let me write that down. So these guys are connected in parallel. So it means that we can replace them with a first in equivalent capacitor. It's not the final, but the first in the process. So it means that I can redraw this picture. And again, the rest of the circuit, in this case, this battery and that capacitor must work in exactly the same way. Okay, so we replace this, and instead of these two capacitors C1 and C2, I can introduce the first equivalent capacitor. Let me label it as C12. So since we replaced capacitor C1 and C2, the equivalent capacitor, let me label it as C12. I think it's self-explanatory, right? And C3 is not touched, so it will be still exactly the same C3. So this will be still C3, and the battery must work in exactly the same way, still the same delta V. Okay, so first simplification, and of course now we need to find C12 using, where is it? Parallel. It's this situation, so we need to use that. So first we can find C12 equals to C1 plus C2. It will be 4 plus 12, so it will be 16 microfarads. Okay, let me frame it because at some point I will need it. You will see. Okay, so first step in simplification. Now it's not the, okay, wrong color. It's not the final step. So we'll have to make then one more step. Obviously, these capacitors are connected in series. All right, so I can write these guys connected in series, right? So we need to replace them. We can replace them with one equivalent capacitor, which is going to be the final one. So as a result, I can redraw my circuit one more time. But in this case, it will be final C equivalent. So this will be our C equivalent. And again, the rest of the circuit, in this case, the battery must work in exactly the same way. So still delta V. Okay, and of course we can find the value of C equivalent now using this situation because that equivalent capacitor replaced two capacitors connected in series. So over here on top, I will be able to write this, right? So 1 over C equivalent equals to 1 over C12 plus 1 over C3. Okay, guys, very typical place for mistakes, right? Of course, students when see that they made that mistake and oh my god, they start cursing, right? Calling themselves names, right? So very often they can calculate this part and then they forget to flip. So they used 1 over C equivalent as C equivalent, right? Very, very silly mistake, right? But every semester, I don't know, like 5% of students or close to that made that silly mistake, right? So of course you need to bring to the common denominator and then flip it. Of course, you will end up with this. So it will be C12 times C3 divided by the product, right? You can get that easily, right? So, of course, we can plug numbers. C12 is 16. Okay, I will drop the units. 16 times C3, 2, and divided by this sum, 16 times plus 2. And of course, units will be microfarad. So it will be what? If you cancel it, you will get what? Complicated number. What? Uh, 16
9
over
over
9
7?
it should be. 16 over 9 should be, right? Let me check. Yeah, 16 over 9. 16 over 9 microfarads. Okay, so that's our uh, uh, final equivalent capacitance, but it's only halfway through. Maybe it's even less than halfway. So now what can be you? What can we get out of this? So now we know now we know the value of this equivalent capacitance. We know the value of the potential difference across the battery. It means that we can find charge. We can find the charge taking from the battery. You know what? The problems like this, every time somewhere in the corner, I usually write this formula because now we're going to use this formula written in this form, in that form. So in order to avoid making silly mistakes, I usually write it somewhere in the corner so that I wouldn't make mistakes. So C equals Q over delta V. Let me frame it somewhere. Right. Okay, so now it will allow us to find the total charge taking from the battery, right? So now I can write the total charge taking from the battery, right? So it will be what? Using this formula, so it will be Q equals, which way I label it, Q equivalent or just Q? Let me use Q equivalent. It will be C times delta V. Of course, C equivalent times delta V. C equivalent, it's a 16 over 9 microfarad. And delta V is still the same, 9 volts, because that's the idea behind, one of the ideas behind this method, that when you make this replacement, the rest of the circuit, in this case battery, works in exactly the same way. So all the way up to this point, delta V is still the same, 9 volts. So times 9 volts, as a result, you will get that Q equivalent equals to 16 microcoulombs. Okay, so let me frame it because that's important results, and it's a very important. And also look, so basically that is the charge taking from this battery. But since the rest of the circuit works in exactly the same way, exactly the same charge is taken from this battery, exactly the same charge is taken from this battery, right? So now we know the total amount of charge. If I asked you, for example, from the very beginning at this point, what's the total charge taken from the battery? Most likely you would have hard time answering this question unless you have lots of experience and you can do this quickly in your head, right? But now we found at least something about this circuit. And now it's sort of like we've made the crack in the wall. And now, once you have the crack in the wall, you can start expanding it to see the truth and nothing but the truth, right? So now, using this Q equivalent number, we should be able to find everything which we need to find. So first simplification was done in order to get that. That was our goal. And now, once we know that, yeah, we can start expanding that, start increasing that crack. Which way? Now we will have to use these important pieces of physics. So now this and this are going to be our bridges. First we use this and this formula, and now these pieces of physics. What do I mean by this? So let's start moving backward. First from that circuit to this circuit. Inside of this C equivalent, we have this capacitor and that capacitor, and of course they are in series. Which piece of physics is correct for capacitors connected in series? This is the series case. Charges are the same. Charge in the equivalent capacitor equals to the charge in this capacitor and charge in that capacitor. So now we will have to use this. And as I said, usually at this point, 60 or 70% of students started writing some very often something which is not correct, right? Up to this point, everything is usually fine. But now, from this point, lots of wrong stuff. So now I need to use this bridge. I can write that Q equivalent equals to Q12 equals to Q3, because that Q equivalent replaced what? This capacitor, you see the subscripts 1, 2, and that capacitor, you see the subscript Q3. And we also know that Q equivalent is 16 microcoulombs. So I can write over here at the end, it is equal to 16 microcoulomb. So that's the bridge which is going to take us from that simplest circuit to this intermediate one. And so, look, now we know the value of charge in the third capacitor. Q3 equals 16. So now you know C3, you know Q3. Can you find the potential difference across that third capacitor? Easily, from this formula, connecting all these three parameters. So delta V will be equal Q divided by C. So we can find now delta V3, right? So now I can get delta V3. Delta V3 equals, again, that's why I told you I need that formula somewhere in the corner so that I can rewrite it properly without making silly mistakes. So delta V, it will be Q divided by C. So it will be Q3 divided by C3. Q3 comes from the bridge. C3, it's given in the problem. Okay, so it will be 16 microfarads divided by the value of C3 is here, 2. Oi, microcoulombs. What did I write here? And you're not screaming at me, right? It should be microcoulombs, right? Over here. I got too excited about getting some results. Microcoulombs, of course. And over here, of course, the same. Microcoulombs. And divided by 2 microfarads. Of course, we're getting 8 volts. So that's the voltage drop across the capacitor 3, 8 volts. So now we can say we know everything. We finished analyzing C3 because we know the charge and we know the potential difference across the third capacitor. Okay, we're done with the third capacitor. And of course, we still need to find the information about C1 and C2. So it's only we're done with C3. Okay, so now, but of course, in exactly the same, we can find now potential difference across C1 too. Although you don't have to do it, right? Because you should be able to tell me immediately what will be the voltage drop across that one. If 9 volts provided by the battery, 8 volts across this, of course 1 volt must be across that one, right? But let me still use the same formula, this formula. Okay, so now I can write in exactly the same way. So delta V 1, 2 equals to Q 1, 2 divided by C 1, 2. Again, Q1, 2 will come from the bridge. All right. C1, 2, that's why I framed it. So it will be easier for me to find. Right. So Q1, 2 is 16 microcoulombs divided by 16 microfarads. As a result, you will end up, okay, let me step away slightly, will be equal to 1 volt. Okay, so we extracted everything that we can from this bridge. So now I need to separate this, and we need to start using the second bridge, which will lead us from this intermediate circuit to the original one. Right, so now this, and because what? We found everything that we can about C3, but inside of C12 there are still plenty of information, because inside of this equivalent capacitor C12 we have these two guys hidden, right? So we need to reveal that information. And of course, since this replaced two capacitors connected in parallel, which bridge we have to use in parallel, potential differences are the same. Potential difference across an equivalent capacitor equals to the potential differences across capacitors connected in parallel. So the bridge will be equal as a result. Delta V12 equals to delta V1 equals to delta V2, and delta V1 comes from this. The value of delta V1 we found in the previous step. So, of course, this will appear over there. You see, everything is linked, connected. That's why I like presenting the problem in this way. When I saw it in this book, actually, I found it very, very convenient. So it will be equal 1 volt. Okay, so that's the bridge now, which we have to use in order to reveal the rest of the information. All right, so, okay, let's start with C1. So now we have the potential difference across the C1. We know the value of C1, so we can find the charge. Again, every time you see where I have to use that formula, rewritten in different ways. All right, so now I need to get charge. So it will be Q1 equals to product C times delta V. C1 times delta V1. And delta V1, as I said, comes from the bridge. And C1 is given from the very beginning. 4 microfarads times 1 volt equals to 4 microcoulombs. 4 microfarads times 1 volt equals 4 microcoulombs. So that's the amount of charge in the first capacitor. Now the second one in exactly the same way. Right. So Q2 equals to C2 times delta V2. And again, delta V2 comes from this bridge. C2 originally given 12 microfarads. So it will be 12 microfarads times 1 volt equals to 12 microcoulombs. That's it. So now we know everything about C1, Q1, and delta V1. Then we know everything about C2, Q2 and delta V2. And over there, we found everything about C3, Q3 and delta V3. Done. Again, as I said, 99% of students have no troubles in getting to this point. But after this, in this part, it's a mess.